Assalamu alaikum, dear students. Good morning. Today we are going to start a new chapter that is moving charges and magnetism. In the previous lecture topics, we have stated about the charges at rest and the electric field associated with them. We have learned the techniques to calculate the electric field in different situations. Now we will be studying the moving charges or currents. Moving charges and currents and the magnetic field associated with them. It was considered in the development of physics that this electricity and magnetism they were situated as separate branches of physics. Their development was independent. But the Oersted experiment in 1820 it changed the course of thinking, and it was revealed that the magnetism and electricity they are manifestations of same charge, while this electric field is associated with a charge at rest or in motion, but magnetic field exists only when the charge is moving, and we will further see today that only when the flux changes. If we change the flux, electric flux, there a magnetic field is produced. Oersted did a simple experiment where he observed that there was deflection in compass needle when it is brought near a conductor carrying current. We can perform it on labs or at home. Very simple. We take a cardboard, pass a conductor through it, connect the conductor to a battery through a key, and take a compass needle near it. We will see that when current is not passing through the conductor, the magnetic needle of the compass is at rest or it is in north south direction. As soon as we close the key, we see current flows through the conductor. Then we see that this magnetic needle is deflection in some direction. And when we reverse the direction of the current, we see that the direction of the compass needle is also reversed. So this simple experiment reveals that there is some sort of relation between current and the magnetic field because a needle is always deflected when there is a presence of magnetic field. We can perform this experiment in another way. Instead of a compass needle, we can sprinkle iron fillings on the cardboard, and we, as soon as the current is passed through the conductor, we gently tape the cardboard. We will see that these magnetic fields they are aligning in concentric circles, depicting a formation of magnetic field lines. So two things here. One is that due to a straight conductor, the direction field, the shape of field line is concentric circles. Second, that whenever we pass current through a conductor, there is a manifestation of a magnetic field. We also know that the direction of the field is given by the tangent to the field lines. We can use in general situations thumb rule, right hand thumb rule to find the direction of magnetic field produced by currents in different situations. If we have a current, straight current, we align our thumb in the direction of the current and our curling fingers will give the direction of the magnetic field lines and tangent to those field lines at any point will give the direction of the field. So if the current is passing from below to upwards, then we will see that the fingers tip in the anti-clockwise direction. If the current is flowing from up to down, so we will see that the direction will be clockwise. Or we can use it in another, we can, if we stretch our fingers perpendicular to the thumb. If thumb represents the current, then the direction of the fingers represent the magnetic field. Magnetic field and magnetic force. Magnetic field and magnetic force. Magnetic field, just like electric field, is the space around a moving charge or a current flowing through a conductor where the magnetic effects are felt. Electric force is it given by product of charge and the electric field, whereas the magnetic force due to a charge is proportional to the directly proportional to the charge amount of the charge flowing, and it is proportional to the velocity component along the direction of the field, and it is directly proportional to the magnetic field strength. So we can combine and we can get that magnetic force due to a moving charge is Q V V sin theta, where V sin theta represents the component along the direction of the field. We can also write it F is Q into V cross B. So the direction of magnetic field can define the vector product V cross B. So direction of magnetic force is perpendicular to the plane containing V and B. Again, we can use Fleming's left hand rule, or we can use the right hand palm rule. Fleming's left hand rule states that if we stretch our forefinger, middle finger, and thumb at right angles, then forefinger represents the direction of the field, middle finger represents a velocity vector or direction of the charge, and then the thumb gives the direction of the magnetic force at that point. Right hand palm rule is if we stretch our hand such that Thumb is that gives the direction of the motion of the charge. Fingers point in the direction of the magnetic field. Then the palm gives the direction of the force. We can consider since direction depiction of the magnetic field line is perpendicular to the page by a cross by a dot and field line is going into the page by a cross. So if it is if a field is represented by crosses, then we see that the field is away from you, and when it is represented by dots, we see that field is coming out of the page towards the observer. Here is a table which shows the approximate magnetic field strength. At the surface of the neutron, theoretically it has been found that the magnetic field strength is 10 raised to power 8 Tesla. Near a magnet, it is greater than 200 Tesla, and near a superconductor magnet, it is 5 to 20. Where at the pole, near a pole of rare earth permanent magnet, it is 5 in 10 raised to minus. Near a pole of a common Bohr magnet, it is 10 raised to minus 2 Tesla, and at the Earth's surface, it is 3 to 5 in 10 raised to minus 5 Tesla. We have the unit of force, magnetic force, it is Tesla. In SI, it is called Gauss, and one Gauss is 10 raised to minus 4 Tesla. From the relation, we see that 1 Tesla it is 1 Newton per coulomb per meter second, or from the formula you can see that B is equal to F. B is equal to F divided by VB sine theta. So we can define 1 Tesla as that much force 1 Tesla is